Welcome to our first video for grade 11 chemistry. We're going to start in our first unit about matter, chemical trends, and chemical bonding, and sort of figure out how different elements and compounds bond together to basically dictate the properties of those substances. So I have this slide here on the history of the atom. Now what I've got is a picture of sort of the history that I'm sure you guys have all seen before. It starts with Dalton over here, who had that billiard ball model that basically said that all atoms are just these little particles that are kind of like balls. Then Thomson came around and changed it, Rutherford changed it, Bohr changed it, and now we're looking at a modern quantum cloud model. These are all important things. And if you take a look at this slide here, this is sort of a more basic diagram. On your notes, what I would like you guys to do is just know the difference between the two and know what order they come in. So note that Dalton's model didn't have anything to do with protons and neutrons and electrons, whereas Thomson figured out that there were positive and negative charges in the atom. So he cut sort of, it looks more like a chocolate chip cookie with all these random charges all over the place. Then Rutherford came along and discovered that Thomson was right, there are positive and negative charges in an atom, but that the positive charges are centered in the center, which he called the nucleus. Then Bohr came around and said, Rutherford's right, but the electrons are not just floating around randomly, they're actually in these energy levels, so he drew them in circles around the nucleus. And now the most current and I guess most used model right now is the charge cloud model or the quantum mechanical model of the atom. That is something that you're going to learn a lot more about in grade 12 chemistry. But this is basically all you need to know. So if you want to draw a little picture and add in a little description for each model, that's pretty much all you need. So now we're going to do a quick review on the structure of the atom. What is an atom actually made up of? So hopefully you remember that we have three different types of subatomic particles that we look at in this course. Protons, neutrons, and electrons. Hopefully you also remember that your protons and neutrons are inside the nucleus. Your protons have a positive 1 charge, your neutrons have a neutral or no charge, and then your electrons have a negative 1 charge, and they float around outside the nucleus. All atoms of a particular element have the same number of protons in the nucleus. That's really important, so you should put a star or highlight that point there. An element is actually identified by the number of protons it has. So if something has 6 protons, it is always 100% of the time carbon. If something has 2 protons, it is always 100% of the time helium. If you change the number of protons, you change the element completely. So that's very, really important. An atom is also neutral, which means that the number of protons that are positive have to equal the number of electrons that are negative so that the charges balance out. All right, next up, the atomic number and the mass number. These, again, should be review for you. They're off your periodic table. So what I've got here, right here, is the symbol for sodium, the standard atomic notation for sodium. So you can see that sodium, the symbol is Na. The atomic mass, which is the bigger number, is up on top, and the atomic number, which is the smaller number, goes down at the bottom. So if you look over here, what is the definition of your atomic mass? That is the number of protons plus the number of neutrons. We don't include the number of electrons in there because the electrons don't weigh very much at all. In fact, they are so small that their mass is pretty much insignificant. So that's why we only really count protons and neutrons in the actual mass of the atom. The atomic number always tells you the number of protons. So for sodium, let me see. Oh, I can't actually type in here. Shoot, okay, I'm going to write. This is going to be messy. So for sodium, we actually have 11 protons. So 11 protons. Oh, that's terrible. I'm sorry for my writing. We will have 11 electrons because it's neutral. So we have 11 electrons. And how do we figure out the number of neutrons? Well, we have to take 23 minus 11. So we actually have 12 neutrons. This is terrible. I gotta get me a better pen. All right, so electrons of the atom. So you guys learned this fancy dancy little model over here last year. That's called a Bohr-Rutherford diagram. And that is still accepted Not because it's right, but just because it's a really easy way to visually represent an atom. So we do still use it even though we know it's wrong. We know now that electrons exist in energy levels, or these electron clouds, around the nucleus. So it's not like planets orbiting the sun and these electrons are going around and around in circles. They're actually in a three-dimensional cloud and don't necessarily travel in a circle. They travel a lot more randomly. So to simplify the drawings, we do draw these energy levels as rings around the nucleus, but if you look over here, these are actual electron clouds. So this red cloud here is basically an area where we might find an electron. Here, this blue cloud here is an area where we might find an electron, and a green cloud here is an area where we might find an electron. These are all different energy levels. When we overlap them together, we get this model here, which is a lot more complicated to try and draw. I will never expect you to draw that, but it just kind of gives you an idea of what the atom actually does look like. And like I said before, you will study this a lot more in grade 12. Lewis dot diagrams can also be used to show the valence electrons of an element. And they're useful because only the valence electrons end up interacting when atoms bond to form molecules. So anytime we make a bond, it's really only the valence electrons that make a difference. So how do we draw a Lewis dot diagram? You do need to know this. Write the element symbol, and around it draw dots, one for each valence electron. The dots should be spread over all four sides. Excuse me, dots are not paired until all sides have at least one dot. So it doesn't matter on which side the dots are placed. For example, hydrogen can be drawn four ways. So there's my hydrogen. So we draw the symbol in the middle, and then we draw the dots around. So hydrogen has one valence electron, so we can draw it up on top. Or I can erase that. We could draw it on the side here, or on the bottom, or on the other side. It doesn't matter which way you draw. Forming ions. The shell of an atom is full if it has 8 electrons in it, except for the first shell, which is happy with 2 electrons. So remember the 2-8-8 rule. Atoms are more stable if their valence shell is completely full or completely empty. And when it does this, it has what is called a noble gas configuration, which means that its electrons look exactly like the noble gas it is closest to. So an atom may gain or lose electrons to achieve a noble gas configuration. And in this case, the atom would become an ion or a charged atom. So let's look at an atom. So let's do, say, beryllium. So beryllium usually has just trying to get this to work properly. There we go. So beryllium has 2 dots around it. 1, 2. But it is much happier if it has a full valence shell. So that means it can either gain 6 electrons to fill that up and have 8 electrons, or it can lose 2. So what it actually does is it ends up losing 2 electrons, and then we get what is, so once it loses those 2 electrons, it has extra positive charge in the nucleus, so it'll have a Be2 plus charge. And again, this should be reviewed from grade 10. Isotopes, this might be a little bit new for you. An isotope is an atom of an element that has the same number of protons, so it's the same element, but may have different numbers of neutrons. So for example, hydrogen actually exists in 3 isotopes. The first one here with only red dot basically has only 1 proton and no neutrons. That's sort of its most common isotope. The second one has 1 neutron, and the third one has 2 neutrons. So their masses are going to be different. This is going to have an atomic mass of 1, this one will have an atomic mass of 2, and this third one will have an atomic mass of 3. But because they each still have 1 proton or 1 red dot, it's still hydrogen. So think of it kind of like twins or triplets, so in this case triplets, and one or two of them are a little bit heavier than the other 2, but they're all genetically identical. So that's sort of how I look at an isotope. So because protons and electrons determine an atom's chemical behavior, isotopes will have the same chemical properties, but their physical properties are determined by mass, so isotopes may have different physical properties. So that's when we get into this new topic, which is average atomic mass. So our average atomic mass is actually listed on the periodic table, and that's why on the periodic table you will see a lot of elements that have decimal places in their atomic mass. That's because that mass is an average of all the isotopes that exist. So the symbol is this fancy little U with a little tail on it. That's called a mu. And one of those is equal to 1.7 times 10 to the negative 24 grams. That's a really, really small gram. It is also equal to 1/12 the mass of a carbon-12 atom, which means that it would represent the mass of one proton or neutron. So try this activity if you want at home. We're going to look at it a little bit more in class. If you have 10 marbles, there are 5 blue, 3 red, and 2 green. If the blue marbles each weigh 4 grams and the red marbles each weigh 3 grams and the green marbles each weigh 2.5 grams, find the average mass of one marble. It's kind of a tough question. If you want to pause the video and try to figure that out, you can. All right, here I'm going to show you a calculation on average atomic mass. What I'm going to do for today is stop this video. I'm going to do a second video showing you how to do this with a pen that actually writes better, because right now I can't write. So I hope you enjoyed the first video, and I will post a second link for these calculations for you to watch later on.